hour we're going to discuss how the cosmos may have come into existence. So we took a tour of the universe, a very brief one last hour, and some of the things we learned is that our Milky Way is not the only galaxy. There are approximately 100 billion galaxies and 100 billion stars per galaxy. So they're like 10 to the 22nd power, one with 22 zeros behind it, stars. The expanse, energy, and complexity of the universe is simply beyond human comprehension. Stars are born and stars die. There's a cycle, a life cycle for stars. And we found out that the universe is expanding. So the question is, what does all this mean? How does this affect our understanding of nature and of Scripture? That's what we want to look at, begin to look at this hour. So there are a few logical possibilities. It's surprising. There are very few logical possibilities. Either the universe is eternal or it is not eternal. And if it's not eternal, it had a beginning. I don't know of any other logical possibilities at this level. For most of the scientific era, beginning in 1600s up until very recently, number one was the consensus of the scientific community. There are some advantages to that. If the universe is eternal, then it didn't have a beginning, and you don't have to worry about the sticky problem of how it began. So there was a great motivation for the universe to be eternal. Now, eternal means that the universe had no beginning, and it will not have an end. That can be accomplished several ways. The simplest being a static universe, a universe that never changes at all. But last hour we learned that stars are born and stars die. They're constantly changing. So a static universe is not going to work. This is something that was thought about by Aristotle about 450 BC. And it enables a very simplistic picture of the universe, very easy to explain. And as I say, it avoids the messy problem of a beginning. But, of course, stars are born, remember, and stars die. So the universe is not static. It is changing. But it could still be eternal because stars have a life cycle. The universe could be what we call steady state. Think of a huge soccer stadium, holds 100,000 people, and a few people, a couple of hundred, get up to go to the restroom. But as they leave, a couple of hundred people come in. So the number of people in the stadium remains constant. So the universe could do the same thing. It could be eternal if for every time a star dies, another star is born. It wouldn't change overall. It'd be like the stadium. The population of stars would remain constant. So individual stars would go through life cycles, but on average, the universe wouldn't change. It'd be the same size, contain the same number of stars, and have the same total mass and energy. Well, that's a problem too, isn't it? Because Edwin Hubble, remember, observed that the universe was expanding. The galaxies that he could see are moving away from us. So it's not steady state. The universe is expanding, then it could be unchanged or even on average, but could still be eternal with an oscillating model. And this is like when you throw a ball up in the air, and it goes up and gravity's acting on it. It slows it down until it stops and it begins to fall back down. So the universe, it exploded, had a beginning there, exploded, and it's expanding outward, but it's being pulled back by its composite gravity. So it's slowing as it goes out, and it's going to come to a stop someday, and it's going to collapse back into a great crunch, which will trigger another big bang. which eventually would stop and come back, and there would be another great crunch, another big bang, and so it would go on eternally, oscillating, the oscillating universe theory. So this seems to work until, of course, we found out that the universe is not only expanding. More sophisticated measurements made more recently have found out that it's not just expanding, it is accelerating. You throw the ball up, and instead of slowing down and coming back, it actually gets faster and faster. The universe is never going to contract. It's never going to come back and form a great crunch. It's a one-way process. And so now, it's now recognized that the universe will never contract, that the oscillating universe theory didn't work. It's firmly established now that the universe is not eternal. It had a beginning. Interesting, isn't it? Moses told us that first 3 words of Scripture 3,500 years ago. 3,500 years ago, modern science has finally come to agree with Moses. The final nail in the coffin for the eternal universe was the second law of thermodynamics. It was discovered by engineers trying to improve steam engines, but we know today that it applies to much more than steam engines. It applies to virtually everything in the universe, every kind of system, not just thermodynamic systems, but electrical systems, biological systems, all kinds of things. So the universe is a closed system, and according to the materialists, take them at their word, and therefore, according to the second law of thermodynamics, if it is a closed system, any event that occurs in the universe will result in greater disorder. That's what the second law says. Anything you do will produce waste heat or some form of disorder. The universe is moving from order toward chaos, and it can never retrace its steps. This is Robert Jastrow. He's a world-famous astrophysicist, and he has come to this conclusion. He says, now there are 3 lines of evidence: the motion of the galaxies, the laws of thermodynamics, and the life story of stars. We've talked about the motion of the galaxies and the life story of stars. We'll talk more about the laws of thermodynamics. But all 3 point to one conclusion. All 3 indicate that the universe had a beginning. So our first observation, there was a beginning, and that's important. Now, the galaxies have been observed to be moving away from each other, and the most distant are moving the fastest. This is the signature of an explosion. If you have an explosion, the material at the center doesn't move very much because all the material around it is pushing out. But the material on the outside is pushed by all the material behind it, so it moves the fastest. That's the signature of the expansion of the galaxies. So because of this came the idea of the Big Bang. So given that they're moving away from us and from each other, it's reasonable to reverse time and see what happens as we go back in time, like playing a video backwards. You can think about that easier back in the times when we had film. But if we play it backwards, then what happens is that today the universe is smaller than it's going to be tomorrow because it's expanding. But if we go backwards, it's bigger today than it was yesterday. The galaxies are further apart today than they were yesterday, and further apart yesterday than they were the day before. So you see kind of what's going to happen. When this is done, the galaxies move closer and closer and closer together as we go back in time until finally they converge to a single point. So everything, if you think about what this means, all the mass and energy of the entire universe, of 100 billion galaxies, on average having 100 billion stars, existing on a single subatomic point. In mathematical terms, it's a singularity, a point with no volume. And all the energy of these stars is at that point. A highly unstable condition. And so what would happen if you had all that at one point? It would explode. So the idea of the creation coming from a single point and the ignition of a Big Bang came into being. So initially all this matter was there at a single point, and the logical initial conditions, if we can talk about that, was that you would have infinite mass energy. Remember, mass and energy are different forms of the same thing. That's what Einstein found, that M equals mc squared. It relates mass and energy. So they're not two different things, they're different forms of the same thing. So the universe consists of mass, energy, space, and time. And everything in the universe was at this single point in zero volume. And this, as I said, is extremely unstable. The observed increase in radial speed of the galaxies with distance from the Earth is precisely the characteristic of an explosion. You can think about it as you're making raisin bread, and you got raisins in the dough, and you put the dough out and let it rise, right? I think that's what you do. And as the dough rises, what happens to the raisins? They get further apart. So the universe, the idea is that space is expanding, and it's carrying with it all of the galaxies. So from our observation, it appears that the universe began at a single point, and that this point was the source of a gigantic explosion of unimaginable force and energy. So high explosives, if you think about it, for example, a nuclear bomb, produce a tremendously hot fireball. And so it was thought back in the 1940s, when this theory first was emerged, that, well, if there was an initial Big Bang, it should have produced a fireball. And what they were looking for is, since nobody was there to observe the Big Bang, what would it have done that would be a signature of this tremendous explosion that might be observable today? And so they began to think about this fireball, the flash. An atomic reaction creates, a bomb creates a flash. You're not supposed to look at it. So it was predicted back then in 1948 that the explosive beginning of the universe would have created this gargantuan, super hot fireball and a flash. And the flash would be in the form of gamma rays, the most energetic form of electromagnetic radiation. You know, light, radio waves, microwaves, gamma rays, X-rays, they're all the same thing. They're just different frequencies. So, and we see them different. We can only see a little narrow band of this huge, huge thing of electromagnetic radiation we call visible light. But below there you have infrared, and right above it you got ultraviolet, and then you got X-rays and gamma rays at the top. So this super hot fireball would have initially produced this flash of gamma rays. But electromagnetic radiation is waves. And if you have a wave in a medium and the medium is stretching out, what happens to the wave frequency? The wave gets longer, doesn't it? And so it gets shifted from gamma rays until today, it should be microwaves, a very slow vibration. And so they began to look for this. In the waves, it should be microwave radiation, and we have ways of detecting that. And they call it the microwave background radiation. Everybody was looking for it. It was detected first in 1964 by two American engineers from Bell Labs. They were out trying to work with communications with satellites, and they kept getting this noise. And everywhere they looked, they got this noise. Meanwhile, at I believe it was MIT, there was a group that were looking for this microwave radiation. So these two engineers found it, and they got the Nobel Prize, not the guys at MIT. But it was found finally in 1964 a number of years after it was predicted. That's interesting, I think. So the cosmic microwave background was finally broadly accepted after NASA launched what they call the COBE mission in 1992. It was a space mission designed to map out the microwave background. And what they found is it is very uniform to about 0.005%. Pretty smooth. And that means that it could not have come from nearby stars or even galaxies, because it would be more bumpy than that. So it is precisely what was predicted as the beginning of the Big Bang. So I'll exaggerate it. It's 0.001%, 0.001%. And it matched what they predicted, and it eliminated the possibility of a stellar or a galactic origin. So accordingly, the cosmic microwave background has been broadly interpreted to be the remnants of the primordial fireball of the beginning of the universe. So there was a beginning. The creation expanded from a single point, and there was a primordial fireball that originated at that vicinity of that point. So it's also been found that the cosmos exists of three primary things: matter energy, which are different forms of the same thing, space, and time. And all three are thought to have emerged from the Big Bang, from this initial condition. So it's not exactly like we think of a bomb goes off and the shrapnel expands out into space. The Big Bang, since there was no space and no time, carried space and time with it. It's a little bit more complicated and a lot harder to think about. So, what are the laws of nature? Well, the laws of nature are nothing more than our observations of how these three entities, matter, energy, space, and time, relate to each other. And as I said earlier, a law of nature doesn't do anything. It's just the way things are. It's a relationship that exists for some reason. All right, so the universe consists of three basic constituents. So we come back to our logical possibilities. Now we eliminate the eternal universe, finally, and the universe is not eternal, and therefore it had a beginning, and the question then is what happened in the beginning? And again, there are only two logical possibilities, interestingly enough. Either the universe created itself, or it was created by something else or someone. The only two possibilities I know of. If it created itself, that's an interesting problem, because since time and space are also created things, it would have had to create itself not only before it existed, but before there was any time or any space. The materialists have a real problem, bless their hearts. The problem they have with the second possibility is we know who the someone is, don't we? So there are other questions that any attempted explanation of how everything came to be have to answer. And the first is a simple thing to ask: why is there something rather than nothing? If there originally was nothing and you did nothing, there would still be nothing. But it brings up an interesting and very difficult question to answer. How did something come from nothing? Anybody want to offer an answer? The second one is similar. We just spent an hour a while ago looking at the beautiful structure, complexity of the universe. It's very complex, it's very structured, it's ordered. Why is the something structured the way it is? So the attempt to answer these two questions that today is the Big Bang Theory. You've probably all heard of that. So let's talk about the Big Bang Theory a little bit, and we're not going to do any mathematics, but we're going to talk about what its basic tenets are, and that's pretty simple. The Big Bang says that the universe began in an immense explosion, or expansion they call it, from which all matter, energy, and space and time originated. And secondly, the order that we now see has evolved, there's that magic word, from that initial chaos. That's the two primary things it claims. And so there's some things we should note here going forward. The theory does not account for the origin of what it was that exploded. Now, if I walk in here and I say, I'm going to blow you all up, and I'm sitting here with my swimsuit on, and you can see I don't have anything, you're not going to be too worried, right? But if I come in here and I've got a stick of dynamite, you might pay a little more attention. If I have the stick of dynamite with a cap in it and some batteries over here, you're going to pay a lot of attention. So you have to have something to explode. And not only that, there must be a reason for why it explodes. Dynamite doesn't just blow up for no reason. A rifle bullet doesn't go off for no reason, thank goodness. And secondly, the theory appears to violate a number of very fundamental laws of physics, which I find interesting. So let's look at a couple of those. There's the law of cause and effect, or the principle of causality. And you've all probably heard this. Every effect must have an adequate antecedent cause. In other words, things don't just happen for no reason. So let me explain a couple of things here. Let's talk about adequate. And we can visualize this. You have a 16-year-old son that's just gotten his driver's license. And so you're allowing him to take his first solo trip in the family car. And he goes out with his buddies, and he comes back, and as he pulls into the driveway, you notice that the right front fender and headlight are all smashed. And you say, son, what have you done to the car? And he says, don't worry, Dad. He says, we were driving down the road over here, below the speed limit, mind you, and there was a dog running along beside the road, and just as we passed that dog, a flea jumped off the dog right in front of the car, and pow, we hit that flea, and well, you see what happened? Would you even tempt that story? You see, the flea is not an adequate cause. It's a cause, but it's not adequate, is it? So how about the idea that the whole universe, that huge star Antares, our whole solar system, our galaxy, 100 billion other galaxies, all came from a little teeny speck smaller than an atom, uncaused. You buying that? Secondly, let's talk about antecedent. Antecedent just simply means that the cause must precede the effect. So here in Alabama, we don't blame today's flash flood on tomorrow's thunderstorm, right? Thunderstorm has to come first. The Big Bang Theory really doesn't account for a cause at all. First law of thermodynamics, it can be stated in a lot of ways, but one way is matter can neither be created or destroyed. And since Einstein did his work, we have to say matter hyphen energy. Matter energy can neither be created or destroyed. It can't. So what happens as you drive your car down to Birmingham, and you put in a tank of gas, and you get to Birmingham, and your tank's empty? What happened to all of that gasoline? You used it. Let's put it a little more technical than that. Gasoline is a very complex molecule, hydrocarbon molecule, made of hydrogen and carbon. And so when it gets hot enough, a hydrocarbon molecule breaks down. And the hydrogen in it breaks off, and it combines with oxygen in the air to form water vapor. That's a gas. The carbon combines with oxygen in the atmosphere and forms that hated gas, carbon dioxide. It's a gas. So that tank of gas is still with us. It's just out in the atmosphere. You didn't destroy anything. You just changed the form of it. How about an atomic bomb? Now we do away with some matter, but what do we get back in exchange? a whole lot of energy. And you can go the other way, by the way. You can take energy and do what they call pair production and create a lot of energy can create a little bit of matter. So matter and energy are the same things, and you haven't destroyed anything, you just changed the form of it. Kind of like when you take a cube of ice out of the refrigerator and you put it on the counter and it melts. It changed from solid to a liquid. That's a little bit simplistic, but nothing we do can destroy or create matter. It's never been observed throughout all of human history by any scientist that we have created or destroyed anything in terms of the basic elements of the universe. So, what does the Big Bang say? The whole universe came from nothing, uncaused. It's not an explanation, is it? The second law is a little more esoteric. It says the total entropy or disorder of any isolated system can never decrease in any reaction. And you all know that, maybe not in those terms. But this has been observed throughout all of human history, not just during the scientific era. Well, what that basically says that things grow old and they die. You know, when I was about 19, I was a collegiate athlete, and I could bench press 300 pounds. I could climb a 20-foot rope in under 6 seconds. I could do a lot of things. I can't do them anyway. I had dark hair, brown hair, you know, and my hair's not just turned gray, it's turning loose. What's happened? Well, entropy is doing its job on me, and it's not through. We know that trees sprout from seeds, they grow, and eventually they die. Rivers create holes in the ground. We call them valleys, right? This law states that everything is going downhill. And the bad news is we have never observed this law to be contradicted. It has always held without a single exception. You can apply it, as I said earlier, to mechanical systems, to thermodynamic systems, to biological systems, to pneumatic systems, to electrical, anything you want to talk about. This law says you're going to go downhill. In fact, without this law, the universe wouldn't work. Why do we get heat from the sun? Because of this law. The sun is burning up its fuel. It's becoming a lot less ordered as it burns that, but one of the byproducts is that some of the heat comes here to Earth. And you say, well, a tree sprouts from a seed and it grows. That's a reverse. That's creating order. That's true. But this holds for a closed system where you have no input of energy or matter. A closed system. The tree is not a closed system. Try turning the sun off and see what happens to the tree. So if you include the sun, you have in the whole system, counting the tree and the sun, an increase of disorder. So that's true throughout the universe. As far as we know, we can't observe the whole universe, and throughout all the time that humans have been here. We all get gray hair. It falls out for most of us, and eventually we go on. Every tree that's ever sprouted has died. So this is a very important law. Now, how does it relate to the Big Bang Theory? Well, the cosmos is closed, according to the materialist. There's nothing else but the cosmos and its laws, the universe and its laws. It's closed. Therefore, this law applies to the universe overall. And the universe, therefore, has to be increasing in disorder. It has to be running down. In fact, science has told us that if we could be here long enough, what we would see is as the galaxies move further and further apart, and as more stars die than are born, the galaxies will go dark. And eventually, everything will be a uniform schmuck. And it wouldn't matter if you went 100 billion miles or 1 mile, you would see no difference. It would be just uniform, stuff. That's called heat death. And that's what science predicts will happen to the universe. So how is it that after the Big Bang, the laws of nature cause the universe to increase, to self-order itself? But now what we observe is that it's falling apart by the same laws. So here's a picture of what's happening. This is a plot. On the bottom we got times, starting at the Big Bang on the left and going forward to the right. On the left we have entropy. Low entropy at the top, which is high order, and high entropy at the bottom, which is chaos. On the right we have order and chaos. And so you have increasing order going up, increasing disorder going down. So perfection at the very top, chaos at the bottom. Over here we have low entropy, high entropy. And so the red curve is what the Big Bang predicts. We start off in chaos, the most gargantuan explosion in the history of the universe. And that explosion self-ordered. It became, from energy, pure energy, it became particles, subatomic particles, which then grouped together and formed atoms, which grouped together and formed molecules, which grouped together and formed other structures. And given enough time, it got more and more ordered, more and more functional. And time passed and we get more and more order, more and more functionality, until finally we have B&W cars, 747 airlines, and you and me. All out of that self-ordering of this chaotic explosion. Entropy tells us exactly the opposite. Now, the red line is the Big Bang theory. The white line is our observation of science. And it says we go from order always toward disorder. And that's bad news for some of us, but it's nevertheless what's going to happen and what has always happened without a single solitary exception. So what you see here is that the two are at diametric odds with each other. So Stephen Hawking, you probably all know Stephen Hawking. I admire the guy. When he was 36 years old, he was working on his PhD, and he was diagnosed with Lou Gehrig's disease and told that he had a year or two to live. And he decided he would go ahead and get his PhD. And he just died just recently. He's basically my age. That's what's happening to people my age. But look what he says. He wrote 2 books, and in his first book was fairly neutral about religion. He says, the odds against a universe like ours emerging out of something like the Big Bang are enormous. And then he went on to say, I think there are religious principles involved. He was being kind of tongue-in-cheek, I think. Sir Fred Hoyle is another world-famous astrophysicist. He says, a common sense interpretation of the facts suggests that a super intellect has monkeyed with physics as well as chemistry and biology. And if we had more time, there are good arguments for that statement. So the problem with the Big Bang in its materialistic version, it excludes any external influence or intelligence. And therefore, it requires the violation not only of Scripture, but of the laws of nature, as we've seen. So, and as I asked a while ago, why should the same laws create order out of an explosion on the one hand and chaos on the other, which is what the universe is going toward? So the point is, any theory that relies on the laws of nature, which are just our observation of how nature relates to itself, if they try to explain the origin of nature, will necessarily be logically inconsistent. It's the mother of all bootstrap operations, right? Shoestring, whatever you want to call it. Laws are simply statements of how the nature works. How can they apply before nature exists? So, the logical possibilities, we eliminate another one. The universe was not created from nothing. It was created by something or someone. So the next session we'll look at how this relates to Genesis 1. Thank you.